It's Paul here with the second half of the Snow Day lecture for Math 23b on what looks like a completely different topic, namely determinants. You already know about 2x2 and 3x3 determinants, but if we want to be able to do integrals in Rn, we have to generalize the concept of determinant to an n by n matrix. Here's a nice way of thinking of such a determinant. You've got n vectors. They're the columns of the matrix, but you don't know which vector is which column. The first of your vectors could become the first column, the second column, anything up to the nth column. And you think of the determinant as a little machine, a black box. It has n slots that can hold your n vectors. We might put the first vector into the second slot, the third vector into the first slot, the n minus first vector into the nth slot, and so on. And when all n slots are filled with vectors, with a different vector going into each slot, a value shows up on the output dial. That value is the determinant of the matrix. This machine has the following properties. First, it's multilinear. If you stuff vectors into any n minus 1 slots, leaving any one of the n slots empty, then when you look at the output, you discover that it's a linear function of what goes into the final empty slot. Second, this machine is anti-symmetric. If you pull vectors out of any pair of slots and replace them in the opposite order, the output changes sign. Finally, normalization. If you take the first standard basis vector and put it in slot 1, the second standard basis vector and put it in slot 2, and so on, the output is +1. Now there's a problem with this sort of definition. It's not clear that such a function exists, and furthermore, it's not clear, given that it exists, that it's unique. And keeping track of all the indices necessary to do these proofs is a bit tedious, as you will see. So, to summarize, we put n vectors into the n slots, we get an output, and we have two questions to answer. First, is there a function that is multilinear, alternating, and properly normalized? In other words, is it possible to build a machine to these specifications? Second, is this function unique? If one of these machines is made in the US and another is made in China, and they both conform to the specifications, will they produce exactly the same result, or is it possible that different machines producing different outputs could meet the specification? The answer is this determinant function exists and is unique, and I will now show you most of that. To show that the determinant function exists, I'm going to use a technique which the Hubbards call development by the first column. You may have learned this under the name expansion by minors. The proof is relegated to an appendix, and what makes it tedious is the first column has to get singled out, whereas in fact you can use this technique on any column, or for that matter on any row. And while it's not an efficient general technique for evaluating determinants, there are lots of special cases where it's absolutely the right thing to do. So here's the rule. The determinant of your matrix A is a sum of terms, and in fact it's a linear combination of the elements in the first column. It'll be something times 1 plus something times 1 plus something times 0. For each element in the first column, the magnitude of the coefficient is the determinant of the n-1 by n-1 matrix you get when you cross out the first column and you cross out the row containing the given element. The tricky part is getting the sign of that term, and here's the rule that I like to use. First, look at the main diagonal, going down from upper left to lower right. Then look at off diagonals that are at right angles to that. Some of those off diagonals intersect the main diagonal where there's an element. Others do not intersect the main diagonal in any element, and the rule that works for expansion or development by any column or any row is if they intersect in an element of the main diagonal, then you get a plus sign. If they intersect in a place where there is no element on the main diagonal, then you get a minus sign. So let's apply this rule to our matrix A. We'll work down the first column. First entry is a 1. We cross out the top row, leaving the determinant 1, 0, 2, 1, and we multiply that by 1. Moving down to the next element, we get a minus sign. Now notice that the signs just go plus, minus, plus, minus, plus, minus as you go down the first column. The only tricky thing is finding the sign for an arbitrary element in an arbitrary column. So we've got a minus sign, we've got an entry of 1, we cross out the middle row, and we take the determinant of 1, 1, 2, 1. Some folks like to take the 1, 1, copy it down underneath the 2, 1, and take the determinant of that 2 by 2 matrix. If you use that rule, you're automatically incorporating the correct sign. Finally, the bottom row has a 0 in column 1, but just for the sake of completeness, that comes with a plus sign, and the determinant is the determinant of 1, 1, 1, 0. Now let's think about A2 cross A3. If we take A2 cross A3, the three entries of that are the three determinants multiplied by the three signs. In other words, when you calculate the middle entry in A2 cross A3, you need a minus sign going with the determinant that results from crossing out the middle row. So A2 cross A3 incorporates the determinants and the signs. It incorporates everything except the entries 1, 1, 0 in the first column. And when we form A1 dot A2 cross A3, we are doing exactly the same calculation, and we get the answer 2. So this rule is a generalization of the rule you learned last term as a vector triple product. Now let's see why this rule has all the required properties. First, we want to show linearity, and the only easy place to show linearity is in the first column. When we multiply the entries in the first column by what we get from the other columns, we are in effect taking a dot product of a vector v. That's generalizing A2 cross A3. And we're taking a dot product of an entry where we can imagine that we have replaced the first column by A1 plus some multiple of B1. This dot product is linear in its first factor. You might want to think of that as the distributive law. We get A1 dot B plus KB1 dot V, and you can see that we've established linearity in the first column. Now we want to show antisymmetry. This is easy to show in the 2 by 2 case, which will be the base case for an inductive proof. If I form the determinant of A, B, C, D, as you know, I get AD minus BC. Swap the two columns, and the determinant is now BC minus AD. So, as you already knew, a 2 by 2 determinant changes sign if you swap the two columns. Now, let's consider what happens if we develop on the first column twice in succession. So we're starting to evaluate this determinant. We're developing on the first column, and the first thing we have to do is take A multiplied by the determinant of that n minus 1 by n minus 1 matrix. How are we going to do that? Well, we'll start developing on its first column, and that says we get F with a plus sign times the determinant of the leftover matrix, which I've called capital A. So, developing on the first column, we have A times the determinant that starts F times the determinant of A and goes on. Continuing down the first column, we have the entry B. That goes along with a minus sign. And once we have crossed out F, again we have an n minus 1 by n minus 1 determinant. And E is the top entry, so it goes with a plus sign. So combining, what multiplies the determinant of this capital A is AF minus BE. Now let's swap column 1 and column 2. Again, we develop on the first column. We start with an E that goes with a plus sign, and that gets multiplied by a determinant that starts out B times the determinant of capital A, and so on. The second term is F. That goes with a minus sign, and we then start expanding on the first column of the remaining matrix. The top term is an A. It goes with a plus sign, so this time we get BE minus AF multiplied by the determinant of A. And if you compare the two results, there's AF minus BE, there's BE minus AF. We got an overall sign change when we swapped the first two columns. Now suppose we swap two columns, neither of which is the first column. Well, I'm going to do this by induction. I'm going to assume that antisymmetry is true for an n minus 1 by an n minus 1 determinant. And therefore, when we swap columns I and J, we're going to swap columns in all the determinants that don't involve the first column. By the inductive hypothesis, we will change the sign for all those determinants, and we will therefore change the sign of the linear combination of those determinants, which is our n by n determinant. Now we're almost done, but we could have swapped column 1 with column K. That's not covered by either of the easy cases. However, I can do that in 3 steps. The first thing I do is swap the second column with the kth column. So the original vectors are now in the order 1, k, going on to 2. And in doing that, I've swapped 2 columns, neither of which was the first column, and I've changed the sign. Next, I swap the vectors that are sitting in the first 2 columns, replacing 1k by k1. I proved that that changes the sign. Now we've got 2 sign changes. Finally, I now have vectors 1 and vectors 2 both sitting in positions that are not the first column. When I swap them, again, I get another sign change, and notice the net effect of these 3 swaps is that the original column 1 moved to position k, the original column k moved to position 1. I've swapped columns 1 and k. I changed the sign 3 times, which is the same thing as changing the sign once. So that proves antisymmetry in general. And now I can show linearity in an arbitrary column k. I've got a vector v sub k sitting in column K. I swap it with the first column. That changes the sign of the overall determinant. And now we know that the determinant is a linear function of Vk because Vk is sitting in the first column, for which we've already proved linearity. So now we've got linearity in general. Finally, I've got to show the normalization property, that the determinant of the identity matrix is equal to 1. I'm going to do this by induction. For a 2 by 2 identity matrix, we know that the determinant is 1. Let's look at the n by n identity matrix. There's only one entry in the first column. It's the top entry, so it goes with the plus sign. It gets multiplied by the determinant of the n minus 1 identity matrix, which by the inductive hypothesis is 1, and therefore the determinant of the n by n identity matrix is 1. So, development on the first column has all the desired properties. It will suffice to define a way of calculating the determinant function. It is in general a terrible way of calculating determinants for matrices larger than 3 by 3 because you end up calculating the determinant of the same 2 by 2 and 3 by 3 matrices over and over and over again. But today I'm not going to show you the efficient technique for calculating determinants. That will wait till Thursday, at which time perhaps we can do it in Lecture Hall A because the snow will not have shut us down. I will, however, show you a second rule for calculating determinants. This one has the advantage that there's an explicit formula. It's a little hard to interpret, but it is nonetheless a formula. It says the determinant A is a sum over permutations of the sign of the permutation times the collection of entries that you get resulting from that permutation. Now you've got to watch this carefully. The permutation I'm going to use is 3, 1, 4, 2. That's a reordering of the numbers 1, 2, 3, 4. That's why we call it a permutation. Our convention is the row index comes first, the column index comes second. So this means what we do for the term corresponding to that permutation is we look at sigma of 1, which is 3, and therefore we use the third entry in the first row. Since sigma of 2 is equal to 1, we use the first entry in the second row. We use the fourth entry in the third row, the second entry in the fourth row. Notice we're using one entry from each column, one entry for each row. Now for the tricky part. What sign goes with that? You almost certainly have seen this rule, by the way, for 3 by 3 matrices. And you know that in 3 by 3 matrices, the rule is if you're going parallel to the main diagonal, you get a plus sign. If you're going at right angles to the main diagonal, you get a minus sign. Here's what I mean by the sign of the permutation. What I mean by the sign of the permutation in general is the number of swaps that has to be carried out in order to get that permutation. But there's a simpler way of evaluating this. First, let's look at the swaps. We want to make that permutation 3, 1, 4, 2. How do I do it? I start with 1, 2, 3, 4, circle 1 and 3 because they're about to get swapped. They change positions. Now I circle 2 and 1 with an eye toward swapping those, and 2 and 1 go to 1 and 2. Now I've got 3, 1, 2, 4. And finally, I have circled 2 and 4 because I'm about to swap them. That third and final swap has converted 1, 2, 3, 4 into 3, 1, 4, 2. Since it took 3 swaps, and 3 is an odd number, the sign of this permutation is -1. If you play around a bit, you'll discover there's a way of changing 1, 2, 3, 4 into 3, 1, 4, 2 by doing 5 swaps or 7 swaps. And this proof I'm doing is a little bit incomplete because I haven't proved that the number of swaps is either always even or always odd. If you want to see that proof, take Math 152 next fall. Now here's the Hubbard's clever rule for figuring out the sign of a permutation. I had not seen this before I read their book. That's actually true of an awful lot that's in our textbook. Look at 3, 1, 4, 2 and look for pairs that are out of order. Well, 1 and 3 appear out of order, 2 and 3 appear out of order, and 2 and 4 appear out of order. The other 3 pairs are in order. 1 comes before 2, 1 comes before 4, and 3 comes before 4. And the rule is, if the number of out-of-order pairs is odd, then the sign of the permutation is -1. The advantage of this approach is that everyone will agree on the number of out-of-order pairs, whereas people will disagree in general about the number of swaps. One person will say it takes 9 swaps, another person will say I did it with 13 swaps. So the out-of-order pairs rule is an unambiguous way of finding the sign of a permutation. Here's an inductive proof that this rule works. Suppose you've got a pair I and j that you're about to swap, and I meant to say that I is to the left of j, but what I wrote was mistakenly I is to the left of k. Read that k as a j, and I'll fix it before I post the notes. There are 3 different cases for k. Now, I'm assuming that I is to the left of j. I and j could be in order or could be out of order to start with. It doesn't make any difference. If they're both to the left of k and I swap them, they either go from being in order to being out of order or vice versa. So the number of out of order pairs either increases by 1 or decreases by 1. If k is in the middle, life is a little bit trickier. I and j get interchanged. That changes the number of out-of-order pairs by +1 or -1. But notice, I and k also get swapped, a change of + or -1, and k and j get swapped. So 3 pairs change from either being out of order to being in order or the other way around. In any case, the net effect is that the number of out-of-order pairs changes by an odd number. That's all that matters for us. Finally, if k is to the left of I and j, the only pair that changes from out of order to in order or vice versa is ij. It changes by + or -1. So in every case, the rule is the same. If we make a single transposition by swapping I and j, we change the number of out-of-order pairs by an odd number. When we start out with 1, 2, 3, 4 on up through n, there are no out-of-order pairs, and therefore, if we carry out an odd number of swaps, we create an odd number of out-of-order pairs. Let's finish up by seeing how this works in the 3x3 case. In the 3x3 case, there are precisely 6 permutations of 1, 2, 3. I've listed them in the left column. It's easy to see the number of out-of-order pairs, 0 for 1, 2, 3, for 1, 3, 2, or 2, 1, 3. The 2 elements that I've put in a box are the only pair that's out of order. For 2, 3, 1, the only pair that's in order is 2, 3. The other 2 pairs are out of order. Similarly for 3, 1, 2, where only 1, 2 is in order. And for 3, 2, 1, all 3 pairs are out of order. So I can write down the sign of the permutation, +1 for an even number of out-of-order pairs, -1 for an odd number. Now I write down the term just by looking at the entries in the matrix. For 1, 2, 3, I use row 1, column 1, row 2, column 2, row 3, column 3. For 1, 3, 2, I use row 1, column 1, which is a plus 1. Then I go down to the second row and use row 2, column 3, which is a 0. And finally, I use row 3, column 2, which has a 2 in it. You can check that I've correctly worked out all 6 of these terms. Now, how do we form the determinant? We take what I'm calling the term, which is just a product of entries, and multiply it by the sign of the corresponding permutation. In this case, I get 1, 0, negative 1, 0, 2, 0. When I add up these numbers, I get plus 2. That's the determinant of the matrix A calculated by this formula. Briefly, here's why this permutation rule satisfies the properties of the determinant function. We want to show linearity in any column, so instead of having just A sub k as the kth column, we replace it by A sub k plus some multiple c of another vector B sub k. When I do that, each term changes. A, k, comma, sigma k gets replaced by this, but multiplication is distributive with respect to addition. When I combine all the terms, I just get the sum of terms that gives me the determinant with A sub k in column k plus c times the sum of terms that I'd get with B sub k in column k. So that proves linearity. What about normalization? Well, if we start with the identity matrix, the identity permutation has no out-of-order pairs. It contributes a sign of plus 1, and the 1s down the main diagonal contribute a term that's plus 1. If I use any other permutation, I have at least one entry where the row index and the column index are different. All such entries are 0. They contribute nothing. Finally, what about anti-symmetry? Well, if I interchange two columns, I will change the sign of every permutation. I'll convert each even permutation to an odd one and vice versa, and therefore I've established anti-symmetry. So this is another formula that satisfies all the required properties, and that's the end for today. It will turn out the efficient way to evaluate determinants is by column reduction, for which you can substitute row reduction, and I'll show you how to do that on Thursday.